In about 1985, I think it was 1985, I got a job at the Ericsson Computer Science Lab. And this was a newly formed lab, so really nobody knew what we should do. And so we went there and said, well, what should we do? And they said, well, just sort of fiddle around and discover something and try and do what we've done before, only do it a little bit better. And one of the things we wanted to do better was to reprogram or to think about the ways of building large real-time systems. And so I got to look at the way we used to build systems. The AXE system that Ericsson built as one of the first digital exchanges. I think it was came from a series of exchanges that first were built in 1974. And I'm now at 1985, so I was looking at the way we build these things. And I got interested in the architectures of a system that were necessary to make things fault tolerant. And I remember thinking at a pretty early stage that for things to be fault tolerant, you need two computers. I mean, you can't do it with one computer, because if one computer crashes, you're screwed. So if you've got two, then you can make them fault tolerant. And of course, if they're independent and the probability of them crashing is, say, so at the same time, I mean, suppose you've got two computers and the probability that one crashes is 1 in 1,000, and the probability that two crashing at the same time, if they're independent, is 1 in a million. And if you've got 100 of them, it's 1 in 10 to the 3 to 100, 1 in 10 to the 300. So provided you can make things isolated and independent, you can achieve fault tolerance. So I remember going to a lecture in Bournemouth. Well, it was a switching symposium we went to, and I was there with my colleagues. And
it's so hard to hear you in that.
I'm sorry. I shall. Can they screw the sound up a bit? Hello? Can you hear me now?
The mic's just for the recording.
Right. Oh, I see.
It should be, actually.
Oh, okay. I'll try and speak louder. Yeah. So we went to this symposium in Bournemouth, and there were a load of presentations. Everybody's interested in distributed systems that used distributed garbage collection and things like that. And we sat there, three of us, with me and Robert Bearding and Mike Williams. We took turns at asking the same question after every lecture, and it was, well, what happens if one of the nodes crash? And they'd say, well, it doesn't work then. And then we would turn around and say, well, we can't use that then. And so I remember coming away thinking, this is crazy. Either we're crazy or they're crazy, because I didn't really see how you could build distributed systems out of components that were assumed to work. And I thought, well, let's make them completely isolated. And of course, that means that all the data structures involved in that computation must be copied from one to another machine. And then people said, well, copying is very inefficient. So you can't do that. And I spent 20 years telling people, no, yeah, copying is inefficient, but if you want to make it fault tolerant, you have to copy stuff. You can't have dangling pointers that point to another machine, then the machine crashes, and then expect it to work anymore. So put we made systems with no dangling pointers or anything like that across machines, and we just copied everything. And everybody said we were nuts for about 20 years. And then for about 5 years after that, they sort of stopped saying we were nuts. And and then the multi-cores came along, and then sort of all the problems of programming these things started occurring just because there were shared data. I mean, you've got shared data structures across multi-cores, you need mutexes and things like that. And if you have to stop all the cores while you're copying, it's really bad news. So it's going to be really bad news. We have 1,000-core multi-cores, and we have to sort of pull some handle, and we stop all of them just because we want to do some little trivial copying operation. Of course, once you've spread out the data everywhere, you've made the system parallel as well. Okay, or you've enabled parallelism. So what this lecture is about these aspects of a system. So what I'm going to do is just a quick overview, a quick history of fault tolerance, and then I'm then going to talk about the principles. I wrote a thesis in this, a PhD thesis a few years ago, and outlined 6 principles that you had to achieve in order to make a fault-tolerant system. Those principles are, you could do them in any language. I happen to invent a language as well to do them in. That's Erlang. And I'm going to show you then what the mapping between those principles and the language are, because they're made to fit together. I'll show you that stuff, and then I'll just talk a little bit about whether it actually works or not. And I believe it does work, actually, since we're controlling a large fraction of the world's networks with this stuff. Right. So it's all about failure. Well, stuff fails, deal with it. I mean, that's it. No, we can't assume it doesn't fail. It all goes back to, I think, the first person who thought about this was von Neumann, and he wrote what I believe to be one of the first papers about that. And he's saying we should look at systems like biological systems. An intrinsic part of their design should be that they can fail, and we have to live with that failure, and we have to detect that failure, and we have to recover from it. So in order to handle failure, you need two machines, and one machine has to observe another machine. That's like in this little picture. And if you think about that, that implies a couple of things which immediately hit you in the face. One is that you have to be interested in distributed programming because you've got two nodes, or you've got more than two nodes. You have to be interested in parallel computing because they do actually execute programs at the same time. And you have to be interested in concurrent programming. So even if you didn't want to be interested in these subjects, you have to be interested in them if you want to do fault-tolerant computation. There's no alternative. Okay. Now, there's all sorts of impossibility theorems and things come up in distributed computing, and you can't ignore these things. We don't want to break the laws of physics. I mean, if we assume they're synchronous, well, we've just broken a law of physics. There is no, light does not travel instantaneously. It travels at the speed of light. I used to be a physicist, so we can't do this stuff. We have to take into account the laws of physics. Software systems that break the laws of physics will ultimately fail because they are provably incorrect with respect to the laws of physics. Okay, so one of the first systems that was built for fault-tolerant operation was a tandem in 1981. And I didn't actually have a tandem. Some of my friends had a tandem, but I was very jealous of them. And the classic work with the tandem was documented by Jim Gray. And he wrote this classic paper, which is Why Do Computers Stop? And what can be done about it? And it's all about failure. It's all about replicating computations on different machines. This, if you haven't read it, read this paper. I mean, it's extremely good paper. And it lays down a lot of the principles that are still true today. And what Jim did was postulate certain properties about that. And he said, well, if you were to do these in software, software would probably behave the same way. And I'd done, one way of thinking about Erlang and the work I'd done was actually, although I didn't know it at the time, it's a kind of software emulation of the tandem machine. Because they were doing the same sort of things. And in Jim's paper, he said, well, if a computation fails and you just restart it, it'll probably, it might work the second time. In fact, most of the time it does work the second time. This is due to subtle timing errors and things. This is not a mathematical system. It's not a referentially transparent system. It's not a sort of pure functional system where if you call a function with the same arguments every time, you'll get the same return values. You can get timing and you can get all sorts of things happening. If you start a computation off with the same values, it might fail the first time due to some strange sequencing, and the second time it may work. And Jim observed this for hardware. And he thought that software systems would behave pretty much the same. And I think they do. So I mailed him and said, yeah, they do. And he mailed back and said, welcome to the Church of Concurrency, which I thought was kind of fun. I looked up some things about the tandem. Now, it's funny because the tandem was built for fault-tolerant computing. And these are quotes from the Wikipedia, actually, but I've seen them in many other places. And the thing they found about the tandem computer were in some quotes here. It says, behind handling failures well, this shared nothing messaging system design also scales extremely well. Right. And it says here, non-stop systems have more often been bought to meet scaling requirements of extreme fault tolerance. So this is a kind of funny side effect. So they built an architecture for fault tolerance, and then they found it scaled better than other systems. And that's because if you've got a web server or something, if you can manage to scale it horizontally, then you can meet enormous demands. If the architecture is such you can't scale it into independent bits, then you can't scale it horizontally and you can't scale it up. So the key to a design methodology is being able to split computations into completely independent parts. If you've manage to solve your problem by dividing it into independent parts, you can both get fault tolerance and you can get scalable. So I don't really agree with your first statement. So you can either get fault tolerance or scalability. No, you can either get both or none of them. Right.
I try to say fault and sensitivity.
Okay, right. And he says here, or I don't know if this is a quote from Jim, somebody said, it might be a quote from him, these systems have no shared central components, not even a main component. This is the kind of, today it's become almost I don't know if it's a religion. I think a lot of computer people think, okay, I've been telling people, shared memory is evil, do not use it, because it prevents fault tolerance, it itself prevents scalability. So there's quite a few people who believe that. There's a few diehards who still think it's a good idea, but they're dying out as a kind of breed that will be gone in a few years' time. Right. That was, I won't talk about that. It says nothing about fault tolerance. Yeah. One of the things that was possibly wrong with the tandem was that it just sort of did things again. It didn't really have a particularly sophisticated way of organizing computations if they failed. So one of the things we did is start looking at that and figuring out how to do that. And we came to the conclusion it's good to kind of have a model of hierarchical failures. So basically, if you're doing something and you can't do it, you give up, you try again a few times. But if trying again a few times doesn't work, then you stop trying again a few times and you just fail all that. So we evolved this notion of organizing computations into trees and keeping sort of rules over how often you restart them should they fail. And that became a sort of dominant philosophy. In fact, my thesis was on systems that work reasonably well in the presence of failures. I'm very interested in stuff that fails. I want them to work even though parts of them are failing, and that's how we work. Bits of us fail, but we still sort of muddle along and try to make a software analogy of that. So what happens, I had to think about what happens when an error occurs. You can mask it, pretend it didn't occur and try again, or you can do nothing. The do nothing one, crashing later, is horrible. It's not a totally brilliant idea. Or, well, yeah, you could reinitialize it and try it again. This is what Jim said, and that's what we do. Only we add the provision that if we've done that a few times and it doesn't work, then we'll fail that and go up this tree of things. Right. So I evolved this philosophy called "let it crash." Now, this is kind of counter to normal thinking in programming. When I learned programming, everybody said we should have defensive programming. We should check our arguments all the time. C programmer. Oops. Make sure. Oh, damn. Okay. Where was I? Oh, yes. Defensive programming in C is only necessary because you have a single thread of computation. If you have a sequential language and it crashes, you've lost everything. So people who program in sequential languages take enormous care to make sure that their computations don't fail. For Erlang, you have as many processes as you want, and you have you can arrange that processes observe each other. So it doesn't really matter if they fail. If you've got 500,000 processes to do something, what does it matter if a few thousand of them fail? Okay, so it's a completely different failure model. Instead of having one very fast, suppose you want to deliver something, you can have one very fast delivery car that goes around everybody, and then you make sure, because you've only got one, that it doesn't crash or anything. Or you can have thousands of little taxis all sort of bumbling around, and who cares if a few of them crash? If you want a reliable message delivery mechanism, you can have one extremely fast way of going between the source and destination and hope it never fails. Or you can send out 20 or 30 little messengers who kind of bumble around, and one of them will get through. So you have a completely different view of failure. So I think the way that most programming languages deal with failure is a consequence of them being sequential. If they were parallel, you wouldn't think about failure in that way. You would do it completely differently. So this is, yeah, I've said this. We build trees of things. Then there was the observation, well, we can build different types of nodes in these trees. If things depend upon each other, then if you look at the bottom layer, suppose all those things depended upon each other. So if one of them crashed, the other ones couldn't continue. And so we would arrange for one computation to observe the other ones. And if any one of them crashed, it would kill all of them and then restart all of them. That's when they're dependent. And if they're independent, then if one of them crashes, you could just restart that one because it wouldn't matter. That's a sort of and/or tree. The and nodes are for dependent computations, and the or nodes are for independent computations. So, of course, an arbitrary tree can be split into a graph of and or nodes. That's really rather easy. And that's basically what we do when we build fault-tolerant systems. I like to think of it as a guy sort of swimming between islands with sharks on. If he manages to get to the next island, he's okay, and he can swim to the next island. And if a shark eats him, well, it's okay. A new man pops up by magic on the island he's gone from and starts swimming over again. And it all works very nicely. Right. So the cornerstones of fault-tolerant programming are to isolate errors, to make sure that when one thing crashes, it doesn't crash anything else. Because I always used to say to people, it doesn't really matter if I write I prove my program to be correct. It's beautiful. And then some other program just comes along and pang, crashes it. Well, so really we need to isolate these things. That's what processors in the operating system do. And actually, it's even better done in hardware. If I've got one computer in Australia that's not connected to a computer in America, that computer crashing is not probably going to crash the one in America unless we have sort of quantum entanglement or something very strange that will cause that to happen. So the cornerstones of this fault-tolerant processing are to be able to isolate errors, detect them, correct them, and stop the errors from propagating. And then you have to ask the question, is that something you want to do in the programming language, or do you do it in the operating system? And I would say the answer you should do it in the programming language. It shouldn't be something that's done in the operating system. An operating system is... Yes?
Question, what's the difference between the first and the last bullets in that list?
Stop errors from propagating.
Isolationist.
Well, they're similar. Yeah, I would say that. Stop errors from propagating. No, I mean, the isolation means that you know where they have occurred. Right.
You can also do this in hardware, like the Line 3 architecture.
Sorry?
The Line 3, the Spark derivative for spaceborne applications.
Yes. Right. So the 6 rules I wrote in my thesis were the following. I'm going to show you first those rules because they're kind of abstract without anything to do with programming languages. Then I'll bolt them into a programming language, see what happens. So the first one's isolation. I just need this property of isolation as much as possible. I'd really like to do it on physically separated machines. I'd really like, if my system has 1 million processors, I'd really like 1 million processors to do it on. I'd really like them to be physically separated in hardware. Can't actually do that at the moment, but the way things are going, maybe we'll be able to do it in pretty soon. I mean, we're going to see 1,000-core network-on-chip architectures coming pretty quickly. And so we need that isolation. Best in hardware. If we can't do it in hardware, do it in software. Right. Yeah, well, that's obviously why. If they're all nicely isolated and you want 10 nines reliability and the probability of failure, you know your probability theory. It's easy. I could say we made at Ericsson we made this thing, the AXD, and it was got up to 9 nines reliability, and I think then we gave up. It didn't need to be any more reliable. Well, the next thing, you need to support concurrency, obviously, because once things are isolated, they run concurrently. So you need notions of concurrency and be able to deal with it. Bad concurrency models, I think, is something that really makes a lot of programming artificially difficult. I mean, what goes on in the real world are a lot of parallel things. And if you try and map those onto sequential programming languages, it just becomes extraordinarily difficult. There's an awful lot of accidental complexity that's due to that. I look at loads of problems, and they appear to be difficult seen through the eyes of a sequential world, but when you make them parallel, you just isolate the message channels and what's going on, it becomes rather easy. And then you need, lots of computers to do things. You must be able to detect failures. If you can't detect failures, you won't be able to recover from them. I mean, since you don't know that a failure has occurred, you wouldn't know to do anything. So it's an obvious principle that you would need. And, well, just say that. Oh, this should also work across machine boundaries. It shouldn't be something within a machine. If the way things are done in Erlang is, for example, if I'm running ahead of myself. There's a link mechanism which allows you to be told about the failure in a different process. And if you're observing another process and that process does a computation and divides by zero, you'll get told the process will die. There's a divide by zero exception. But if the machine itself dies, you will also see an exception, even if it's on the same or if it's on another machine. So we try and abstract out physical boundaries so that we can view them as software. We don't want a programming model where we have two styles of programming. One works on one machine, and then we have to change the programming model if we have a distributed system. We don't want to have that. It's not enough to detect failure. We need to know why things have failed. Maybe we can just restart them and it will work again, but if we want to improve our systems, we need to put that information into persistent logs and things so engineers can look at it later. One of the questions I answered in my thesis actually was I asked a question: can we make a system that will crash at runtime, recover without the user noticing it, put something in a log file so that some guy can look at that log file 6 months later and figure out what went wrong and then change the software, such that when the software is actually running, the users are offered a reasonable level of service? And the answer is yes. So we can do that. I traced down several examples of that. And it's really cool because we've built systems where people have thought there were no errors in them because they've been offering a high quality of service to the users. And so they've never bothered to look at the log files. And they've looked at the log files and found these things are just crashing and restarting and crashing and restarting. And it's just all bubbling along without anybody worrying. That's rather nice. Stu?
I believe the Erlang movie actually demonstrates that exactly.
Yeah, well, yes, that was back in 92, was it? Something
Available
like
on
that.
YouTube.
Yes. Right. Next thing we want to do is live code upgrade. This is stuff for building really systems. I mean, I see systems as having a stop switch, but no, there's an on button, but there's no off button. They're going to evolve forever once we've started them. We haven't quite got there. The systems we start, we do stop. I think we've stopped. Some systems have been stopped after 6 years because really we did want to stop them. And we really need to build this ability into systems to evolve. And we're going from these sort of separate programs to large amorphous conglomerations of programs that are never consistent and they're always changing. More like biological systems. I don't upgrade. And we need stable storage. If stable storage is there for if we really do crash, if really everything, if all the computers, even though we've replicated, even though we've got 20 computers, suppose they weren't replicated over data centers and all the power went, or suppose they were replicated over data centers and the power for the whole country went out and they came up again later, then you would need something where the data has been carved in stone or however you do it so that when they recover.
Are you talking about write-only storage in the sense that all of storage history is preserved?
No. Well, you've got a choice there. I want to write enough data to recover from. Don't necessarily want all data. Although as it's looking at the moment, probably we should just store all data. I don't know. There are some critical numbers floating around there. One is the amount of energy required to store data, the amount of energy to transmit data, and the amount of energy to compute a result from data. And depending on how they go, we've either got a big problem in the future or we haven't. I mean, if the energy required to store data is less and its growth is less than the energy required to analyze that data, then big data is a complete disaster because the two curves cross like that. We'll never analyze it all, but if computation grows faster than data storage energy, then we will be able to analyze it. And then we have to get the energy down anyway so we don't fry the planet in doing so, but that's a completely different problem. So those ratios are extremely critical. And the answer to my question might depend upon those ratios, because if we can't analyze it all, there's no point in storing it, all the old data. It's much easier to reason about if we store all the old data. But if not, we'll just store the data we need to recover from. Right, let's store stuff forever. Okay, quotes. Do you want these quotes? Yeah, no, I don't know. How long have I got, by the way? Forever, or?
Well, yes, actually till 8 o'clock tomorrow morning.
Oh, right, okay. This was a quote by, I've just got a few quotes from.
The cameras will go off at 5:30.
Oh, I see, okay, right, yeah, right.
And then dinner occurs and.
Not if he doesn't leave. Good incentive to leave.
Yeah, Jim Gray said it was hardware the key to fault tolerance. Software fault tolerance is to hierarchically decompose large systems into modules, each module being the unit of service and the unit of failure. And the failure of a module does not propagate beyond the module. So, I mean, that was the idea I was saying earlier. The isolation of those errors and the stopping them from propagating. That's what Jim Gray said. He also said processes are made fail fast by defensive programming. They check their inputs. If any error is detected, they signal a failure and stop. So I really disagree with Postel's principle. Sort of be lenient with your inputs and generous with your outputs, or whatever he said. No, you shouldn't be lenient with your inputs. If your inputs aren't totally correct, you should just stop immediately. Stop, you sent me the wrong stuff. Because otherwise you get a sort of knock-on effect. It's very difficult to see what's been happening. And you should fail as soon as possible. Systems should be built which do exactly what their specification says and nothing else. If they get outside this specification, they should immediately die, and you shouldn't do anything else. Right. And of course, Alan Kay said, of course, about people have got object-oriented programming all wrong. He said it's just a gentle reminder that Smalltalk is not about its syntax or the class library. It's not even about classes. The big idea is messaging. The big idea in object-oriented programming is messaging. It's got nothing to do with classes and methods. That's just abstract data types and the organization of these things. But it does have to do with concurrency and messaging. Because this is the thing that decouples systems. Messaging is the great decoupler. And messaging is also, if it's proper messaging, asynchronous messaging, it doesn't violate the laws of physics. So if we do that, bear that in mind, decouple things through messaging and don't break the laws of physics, then we'll have something that is reasonable, I think. Schneider had a few quotes on halt on failure. Failure said, we should say these things, we should halt immediately, not continue. Although they were saying these things, the people weren't doing it in many systems, not in practical systems, I think.
Is this Bruce Schneider?
Yes.
Okay.
Yes. Me. Processes are the unit of error encapsulation, and so on. Processes do what they're supposed to do or fail as soon as possible. Processes, failure and the reason for failure can be detected by remote processes. Processes share no state but communicate through message passing. Right. So how do you program all this stuff? Well, how to program 6Us? Well, you could use a library. If you had a programming language that didn't have this stuff, you could stick it in a library. But if you stuck it in a library, you would have things that were sort of logically correct, but not pragmatically correct. You wouldn't be able to make them efficient if you put them in a library. You can only make them efficient by putting them in the lowest possible level of your programming language. And if that doesn't suffice, putting those primitives into the hardware. So if you put the primitives you need into hardware, then this thing will go efficiently. If you put it into the lowest level of your language, it will go efficiently. If you bolt it on top of something else, it will not go efficiently. My colleague Mike Williams said there were 3 things you had to do in Erlang that had to be fast. You had to spawn processes quickly, you had to send messages quickly, and you had to context switch very quickly. So spent an awful lot of time tuning that to make sure that is extremely efficient. If you emulate it in any other way, it won't work. In fact, the first version of Erlang which I wrote was the emulation, processes were emulated using a database written in Prolog. And so context switch actually involved taking your state, sticking it in a database, waiting for the next job to do, and then you lift it out of the database. So it's actually spending all your time lifting things in and out of a database. Concurrency is not doing one thing at a time and storing the intermediate state in a database. That is not concurrency. That's a mess. Right. So Erlang was actually designed for programming fault-tolerant systems. Oh, here we go. So the isolation rule said that. Wait a moment. I mean, processes are isolated by design. This is not something that is done by the operating system or by the hardware. It's done by Erlang's design. That means that context switches are very lightweight. I mean, in a regular operating system, I think of the order of 700 words are moved when a thread context switch occurs. In Erlang, it's about 3 registers are moved because it's all emulated. We've got complete control over what's going on. The processes, by design, cannot damage each other. They can't see each other's memory spaces. And each process has its own stack and heap, and they're separately garbage collected. Something which, at the time, people said was nuts. Sorry?
How can they be very lightweight if they have shared memory? It seems
They don't have shared memory.
And so if they don't have shared memory, that implies there's going to have to be duplication, and that's going to make them heavier weight, right?
I would think so, yes.
Like everybody.
Like, yeah, you would think that would be the case.
I take it the stack spaces are protected by the MMU.
No.
You're not, your stacks, no, there's not a shared memory pool for which all stacks are.
No. Well, I mean, there is a shared memory, the physical memory of the machine.
Right, and the memory management unit prevents stacks from stacking on each other.
If it were the case that we're using different processes, yes, but we're not. We're all in one process. We've just got 2 threads in one process.
So there's stack protection mechanisms?
Yeah, well, that's in software. That's the compiler that has to be right.
Oh, okay.
I mean, it's a compiler that provides the protection. It's not the runtime.
Okay.
If I got the compiler wrong, then it would be wrong.
Okay.
So it's done by software, not by hardware. That's isolation. This thing keeps falling off. Concurrency. Well, in Erlang, all processes are concurrent. Whether they run in parallel or not, that depends on what the hardware is. Of course, if they're on one core, they won't run in parallel, but they will still be concurrent. And if we had more cores than processes, they would be parallel if we've done a good job there. On a multi-core, they will sort of spread themselves out over the cores. You don't need to worry about that. It'll do it for you. To the extent that it does a good or bad job, that's a research problem because every time new architectures come along, we have to fiddle with them and make sure it works. Our goal is actually to have about a 75% utilization. If we had 100 CPUs, we would hope that our programs would go 75 times faster without tweaking them or anything. And for some problems that happens, and for others it doesn't. It depends upon the intrinsic sequentiality of those programs, because Amdahl's law will still apply. Usually I think you can get down to 10% sequential code in a problem without much trouble, and then you might have to work hard to get rid of the last 10%. Depends, very problem dependent. There are 3 primitives in Erlang to handle the concurrency. Erlang is fundamentally, I mean, the sequential part of Erlang is just a simple dynamically typed functional programming language with no mutable variables. There's 3 primitives bolted on top of that. One creates a parallel process, produces a handle to it. That's a spawn function. You give it a function, say spawn this function. You can send it a message, PID-bang message. It actually sends it to the mailbox of the process. Each process has a mailbox. And the receiving process has a little pattern-driven engine that looks at the mailbox. So it can say, when this pattern's in the mailbox, do this. It waits for these messages to occur, and then it does something. So that's the stuff you need to add to a sequential language to make it concurrent. And failure detection. With this thing, I had spawn link. I can create a link between 2 processes. Now, without a link, if one process dies, no other process will be informed. But with a link, if either of the processes at one side of the link dies, the other process will get a message that's stuck in its mailbox. So the link actually is one of the things I've never seen in any other programming language, or that's an innovative thing in Erlang. And it allows this
Do I have it right that Scala inherited your parallelism?
Yeah,
Yeah, okay.
absolutely, yeah. I mean,
So,
they sat down with it and did the same. And said, "Ooh, do it like this." I could say these primitives, they seem sort of easy, but we did actually try a lot of different mechanisms and kind of, there were pragmatic judgments there. It was developed on a machine with 750 kilobytes of memory and 1 megahertz clock, and so I mean, there are a lot of things there for pragmatic reasons. It's rather like the early Unix day. We didn't have enough room to keep all the stuff, so we threw out the stuff that nobody used. And then we had a user group who were great because you could just give them a new version of the language every day, and they didn't bat an eyelid. It's quite nice. And at that stage, if something goes wrong, you can change the libraries, or you can change the language, or you can change the application, so it becomes quite easy to do things. We were a small group, which helped. You can set up this link condition once you've done spawn link instead of link. Then you'll be told about errors. Now, in fact, you have to do something else. There are two types of processes. There are those that, if they receive an exit message, will themselves die and propagate that exit message to the other processes to which they are linked. And there are ones which can take care of those and stop that. And the reason for that was the problem that occurred in distributed computing of nailing down zombie processes and killing everything. If you started a computation involving dozens of parallel processes, and that computation depends upon all of them working, and then something goes wrong in one of them, you want all of them to die. And that was a sort of classic problem that was difficult to solve. So, in fact, Mike Williams came up with this idea. It was called the C-wire, which was used in telephones. In telephones, we also had this thing, a load of phones being connected together. There was something called the C-wire. And if you grounded the C-wire, you short-circuited the thing, and the current went up everything, and all the things that were electromechanical, they all dropped, whatever they were doing. And the same principle used to happen in the London Underground at the side of the train. If you looked out of the thing, there were two wires that ran along everywhere. And if the train stopped or something, the driver or somebody could lean out of the window and short-circuit these two wires together. And that would go through all the circuit breakers, and everything would stop. And that's what the link mechanism in Erlang is. It's a sort of thing that grounds everything so they all collapse. But then maybe you don't want everything to collapse. So you can say to this process, hey, I'm a special process, and I will not die. And so this process becomes a firewall. So it doesn't die, and it just gets these messages in its mailbox, and it can do things with it. So that's the failure detection stuff. And yeah, the underlying principle in error handling in Erlang is not to fix errors locally, it's fix them somewhere else. The reason that you can't fix errors locally, and you should not try to fix errors locally, is your machine that you're executing on might be dead. So all this kind of try, catch, and something, that's actually dealing with the error locally. That's not going to work if the whole machine dies. So you don't want a different way of programming software and hardware errors. You want to force them into the same abstract model so that you can deal with it in the same way. You don't want a different programming model if you deploy your application on one machine, or if you deploy it on a network with dozens of machines. You want them to behave the same way, and that's deliberate. So this philosophy of letting somebody else fix the problem is kind of deeply ingrained in the way we build systems. Yes?
Just a clarification, you can deploy on an entire cluster of machines the exact same way you deploy on a single machine? Multiples? Yeah. Okay. Yeah. So when you say it spreads
the only thing that will happen are the latencies and things like that. The message passing times will be different, but the semantics will be the same. Yeah, which is what we do. So of course we set up a laptop with 20 or 30 nodes. Sorry.
That's only in 300-point font.
Sorry?
Saying that the only difference is a little bit of latency between local and remote. That's
some of the failure modes are different as well.
The latency is so much higher.
Yes.
It can be 1,000,
yes.
or 10,000, or 100,000 times higher. That in fact distributing these across a cluster of 1,000 machines could actually run more slowly than just running it on the same machine.
Yes.
So
but semantically,
the idea of trying to design where something runs equally on one machine versus a cluster, to me, feels like a non-starter. The environments are just too different.
Well, semantically they're the same. Pragmatically they're different. So when you deploy it on that one, you're going to have to measure a bit and see what's happening and figure out where to put these things. Absolutely. I mean, you're completely right. But that's a second order effect. The first order effect is to get that software correct and run it on one machine. If it's not running on one machine, you're in trouble. Having done that, you deploy it on a cluster or something like that and measure and see what's going on and see if we need to move things around. Hopefully, we'll be able to automate that in the future. I mean, that's in an area of research at the moment, how you move those things and where you put them.
Sometimes there's 150 cores on one die.
Yes.
In which case, the tightly coupled memory gets these messages zooming in and out in a hurry.
Yeah. We're playing with these things at the moment. It's great fun. Parallel machine's got 64 cores in it, so hopefully it'll have 1,000 cores within, if we manage to make the chip.
Clustering model is the multi-core is a very idealized cluster, right?
Yeah. And then, of course, if we've got this nice model where everything goes, we can talk to our hardware friends and they'll do something to get these latencies down, or if it's possible, or figure out how to move the computations. We'll see. What happens now? Fault identification. Yes. When processors die, this message that comes with them is included in an additional parameter, this Y parameter that's in red. And that's provided by the runtime system. It tries to tell you exactly why it's crashed. You can do whatever you want with that. The usual thing is to stick it in a log and let some engineer look at it later. And if you put good error messages there, or if these are good reasons, you can actually figure out months later what went wrong. The live code upgrade bit, this is quite fun. If you got a module foo, this is Erlang, and you say foo : bar, that means call the latest version of foo, even if you changed the code while it was running. And if you call bar, it means always call bar in that particular model, but don't use the latest code if you happen to change it while you were running. And that allows you to just dynamically patch code while you're running it without changing the namespace or anything, which is kind of convenient. Sort of design fault. If I was doing Erlang again, you could only do it twice. You can't do it 3 times. The reason for that is we had very little memory on the machines we did it. If I was going to do it again, I would allow infinite versions of that and garbage collect all the old ones. I don't want to change the namespace when I'm updating the program or letting it evolve, because other programs depend upon that namespace. So we kind of glue the two together. Stable storage is actually, this is the one thing that is not done in Erlang. It's done in third-party libraries or the libraries we've written. So there's a lot of stuff out there to do this. Manesia is a real-time database that ships with Erlang. And then people have built databases using Erlang. Erlang turns out to be very convenient to write databases in. Haven't quite told you the truth about the immutable data. Erlang's got these shared hash tables, which any process can access. And that's it, because in a database update, we don't want to update the entire world in a purely functional language. We're not religious about this kind of stuff. And so people have built big databases on top of that. 2 of them you might have heard of, REAC and CouchDB. CouchDB was the database that CERN chose to store all the data from the Hadron Collider and contributed to the discovery of the Higgs boson. So that's kind of fun, because I used to be a physicist. REAC is used all over the place for internet scale applications. So a lot of these big things you see on the, I don't know if WhatsApp uses, do they use REAC? They use Manesia. Oh, cool. Yes. I mean, their problem isn't big enough to use REAC. I mean, it's only 400 million people using it at the same time or something. I don't know. Okay. So, yeah, what was I saying? Fault tolerance implies scalability. In order to make things fault tolerant, you have to make sure they're made out of isolated components. If the components are isolated, we can run them in parallel. And hopefully they'll be scalable. Apart from, there will be your problems of latencies and things, they will change. And the failure characteristics will change as well. But we have to have some way of doing it. So we have to evolve towards better ways of doing these things. So Erlang has, yes.
It feels to me like you may be conflating coincidence with causality. And that there are some of the things that you do for fault tolerance that also contribute to scalability, but in general, it's not obvious that principle holds. For example, if you take a consensus-based system like Paxos, which is highly fault tolerant, it's also extremely non-scalable.
Yeah, absolutely. Yes. Yes. But then you don't need Paxos for all problems. You don't need this leadership election and all these kind of things. You need them for some problems. And so I think if they're used as a general workhorse to solve all problems, that won't lead to good architectures. Right, so where have we got to? Erlang's got very lightweight processes, very fast message passing, total separation between processes, automatic marshalling and demarshalling of data. This is actually back to the old Unix pipe thing, or to monads or something like that. You know, the output of one thing should become the input of another thing with as little fuss as possible. In the Unix model, you go through text all the time, so programs are serializing and deserializing things all the time, which is a complete mess. In the Erlang model, there are Erlang terms which are just floating through the system, so there are no semantic mismatches. If you go into a database, you don't have to change the format of what's going into it. That's one reason these databases go very fast, because if you store Erlang terms in a database, they undergo no data transformations to get themselves into the database. They just go straight in. They're like object databases.
No marshalling.
Sorry?
No marshalling?
Well, no, there is a low-level marshalling, and there is a low-level format, obviously, because we can serialize anything.
All right.
So there's a in Erlang thing term to binary, which takes any Erlang term, i.e. any Erlang data structure, that serializes it, and then binary to term, which reconstructs it. But it's not parsing. It's LL0. It's reconstructing a term.
Is there an effort to locate structures sequentially in memory such that the marshalling is essentially nil? In other words, that you can just suck up them?
Yeah, we've tried some of that stuff. Yeah. In fact, the Atom, there's a caching mechanism between systems where things like atoms they're sent the first time. There's a 256 byte cache. And the first time, if the thing has been sent before and in the local cache, you just send a single byte. So you've got like object number 23. If I send you a new thing, I might say, here's a big data structure, and it's called object number 23. Second time I send it, if it hasn't been changed, I just send you a 23. And then I might send you a 0 followed by 23, and then a new data structure to change the cache. So we tried to identify common data structures. And in fact, it went fast. When we haven't published much on that, we published a paper years and years ago, I believe, or I can't remember. We did experiments. It's actually faster than Sun RPC, which was quite cool, because we weren't attempting to be fast, but the caching made it faster, which is, and that's hidden inside distributed Erlang, these caching mechanisms. Yeah.
Question?
Yes.
Can you quantify the speed of message passing? I'm curious, when you say very fast, what that means either in terms of absolute nanoseconds or perhaps relative to the cost of a method invocation, which would be the alternative in many of these systems.
Well, we can measure it.
But you haven't.
We do all the time, yeah, absolutely, yes. Because when we're tuning things, we have to make trade-offs.
Can you remind us about any of those? Any numbers you happen to know off the tip of your tongue?
There's a multitude of different architectures.
Yeah, absolutely, yes.
There's hundreds of different ways of organizing silicon, and people have built multi-cores that do many different message passing approaches, so each one would have different figures of merit.
I got my hands on a 24-core multi-core, one of some of the early multi-cores, and I wrote a simple program, make it a 24 by 24 matrix, and just send 1,000 messages between each pair and fill up the matrix. And I was totally shocked. It went 6,000 times slower between the best pair and the worst pair. And then I talked to the hardware guy and said, whoa, what's going on here? And he said, whoa, this is a cache here, and that's got to do that, and you get a cache miss there, and it goes out there, and it does this. And I thought, wait a minute, that's broken the principle we had earlier. There was the time it took to send a message to a process if you were in the same node was independent of where it was. And then suddenly on these multi-cores it's very different. And then every generation of multi-cores has been different. They've put in cache structures. And the network on chip architectures again are very different. And they are, I believe in them. They're going to come and knock out all the other architectures because all the other architectures are, they're not sort of, So network on chip are very, very regular, so you can fabricate them like large memory chips. I think we'll see 1024 chip core things. And get the complexity of the individual cores down, put a big solid crossbar between them, and very nice. That's what I'm playing with. And also very low energy, which is good. Yeah, so we try to make fast sequential code. Well, fast. Of course, we're not as fast as C or Julia or something like that, but if it's not fast enough, you can call Julia, or you can call C, or Fortran, or whatever your favorite now. Or build an FPGA, or build VLSI if you want to go really fast. I mean,
are you a Julia fan? You seem to be mentioning it. I'm just curious.
Yeah, oh, Julia's great. Yeah, I like Julia. Strict functional code. I mean, if there's any functional programmers here? Oh, well, don't kill me, because it's not actually strict. Sort of more or less. Mind you, Simon Peyton Jones said, well, Haskell's got I/O, and so it's not really strict. And he said, so the only thing it's useful for is heating your house, because the processor gets warm. That's the only strict, pure functional program is good. It can be used to heat your house, because the processor gets warm. It's got dynamic typing and transparent distribution, and you can compose sequential and concurrent code, which is nice. So the unit of composition for sequential code is the function call, and the unit of composition for parallel code is, of course, creating processes and creating pipelines with messages in them. And the properties of all this, well, as I said earlier, no sharing, hot code replacement, pure messaging passing, no logs, lots of computers, functional programming. And in response to a lot of your questions, I would say honestly, what we're trying to do was not to produce an academic thing. We're working for Ericsson. We're trying to make something we can put into practice. So we went around stealing all what we thought were good ideas in the mid-'80s and stick them into a language and see what happens.
So are you playing with parallel chips?
Yeah!
Yeah, okay.
Absolutely. Got them on my desk. In fact, if I wasn't here, I'd be playing with them. So I'm looking forward to I've been going talking these silly lecture things all over the place. And,
so it's $99 is for gets a parallel for, right?
Yeah, and I want the 1024 core one. So parallel, here we come. Yep. Let it crash philosophy. That's I think kind of new to Erlang. It's not how everybody else does it. It's how we do it. Don't handle errors in this. I always talk about doing things in band and out of band. You know, if you try and put the error handling in the same band as the computation, it's difficult. I always think of these things like you have blackboards here. It's wonderful. Or, well, whiteboards. You know, I think of computations like this where sort of, you know, there's some in and some output and some kind of functional relationship between them. But the errors, you know, these sort of they're on a bus here. I think of them like chips. The errors flow on these things, and functions flow on the other things. Think of them wiring chips together. Yeah. This let it crash philosophy, if processes crash, then the Erlang runtime system detects it and should do something about that. The OS should protect the resources across boundaries and things. And the program should immediately crash if they go off spec. And I would say this, that defensive programming is a consequence of a bad concurrency model. It's just, you just wouldn't, if you had a proper concurrent language, you wouldn't do it that way. I think this is the only way you would do it. And in fact, I have met so many people who don't know Erlang, who've converted, they're programming in C++ or something, and they said, well, we needed to invent our own little executives, and we sort of discovered that we needed to group things, and then we discovered we needed to monitor them, and then we discovered we need to, and then we found Erlang and found you'd done all this in 1986. And then some of them adopt Erlang, and then they bankrupt the other companies that are not using Erlang, and so it goes on, which is kind of fun. So we've got no shared memory, pure message passing, remote error detection, all the stuff that I said before. And does it work? Would be an interesting question. Well, here's a little one of many stories. This is. I just brought this up in another lecture. This is the road to WhatsApp. So 2002, Alex Shiplin started building an XMPP server fully in Erlang. 2005, a company called Process One, Michael Raymond formed this company called Process One. Took this little XMPP server that Alexei had written and turned it into some products and things. In 2007, Facebook launched a chat server that was based on that software. It was written in Erlang. In 2008, they deployed it. In 2009, they dropped it, actually, and rewrote it in C++. And I talked to one of the technical people at Facebook. I said, why'd you do that? And he said, well, we had lots of C++ programmers, and we didn't have many Erlang programmers. That's because the universities aren't educating Erlang programmers, which is something you might like to think about. So they dropped it. And but you see, what's his name? Jan Kuam started using Erlang before they'd dropped it. So he got into this little window of opportunity. Kind of, hey, what are people like Facebook doing? Yeah, they're using Erlang. So he started that in 2013. He was tweeting and saying, hey, we're doing 18 billion messages a day. And, another one. Actually, this is not the road to WhatsApp. Various things keep bubbling along like this. And then on the 19th of February, WhatsApp was acquired by Facebook for $19 billion, which is the highest value of any software acquisition. The reason, of course, they're not buying Erlang or anything like that. They're buying the fact that that thing got to the marketplace a lot earlier than anybody else, because this way of programming is actually much easier to program, and you can build stuff quicker, and you'll have less errors in it. And it will be easier to maintain because the code's a lot shorter. So that we've demonstrated many. And that we've seen many times. And I just come back from Strangely, where I gave a keynote, and a guy from Weather Accu, is that right?
AccuWeather.
AccuWeather, yeah. He said, we're using Erlang. I said, what can I tell people? He said, yeah. He said, we're doing 6 billion messages a day to mobiles and things. I said, did you have any problems? No. Do you need any help? Francesco always says, I've always got to ask anybody if they need any help. And then I tell them Francesco will help. Because he was a student of mine who founded Erlang Solutions. And no, don't need any help. It just works. And then I went to Chicago, and there's the Erlang factory there. And there's what was that guy? What was his company?
AdRoll.
I don't know who they are. AdRoll. He was doing 80 billion messages a day or something.
They serve ads.
Yeah.
They serve 80 billion.
Sorry, 80 billion server ads a day are running through these things. So I think this is kind of proof of concept that the stuff does actually work. And then Ericsson itself, the mobile networks, the mobile base stations for smart data are controlled by Erlang. So they're switching all of about half, I would guess, the mobile data traffic is being coordinated by that. That's a control plane. Stu would tell you all about this stuff. The way we build things in datacoms is we have data plane stuff. It's called the data plane here. Data plane. And that's high-speed data. This is 10 gigabits per second down here. You can't do 10 gigabits per second in software. And up here, you've got control plane here. And you can do control plane stuff in software. Traditionally, these two things have been bolted together, and you can't get at this interface, and being sold as very expensive boxes. So all these things you buy, like dedicated routers, DNS boxes, firewalls, anything like that, done by network people, they have bolted these two things together. Right. Well, what's happening now is people are saying, well, hang on, can't we split this and have one, this thing, commodity hardware like a PC, can go into Radio Shack and buy one of the data plane things, and then just use any old bit of software to control it. So that's open flow and network-defined programming and things like that. So these things are coming. And actually, Erlang, in the Ericsson products, Erlang's doing that stuff. Of course, it's not doing that stuff. That's just done in hardware.
With an FPGA in the middle between the two, right?
No, not well. No, I mean down here is FPGAs and VLSI and goodness knows what. I mean that's, but not in between.
Or programmable switches.
Yeah. Yeah. So I think that, I don't know. Yeah. Oh, yes. So the answer to my question there was sort of yes, pragmatically. Yeah, this stuff does actually work. Which is possibly why I'm standing here and telling you about it. I don't know. The future. What's happening in the future? Well, yeah. We've got to solve the world's energy problem. We're engineers. We don't want to fry the planet. So I'd really like to move these processors and the switches and things onto solar panels and just get the energy use down to a sustainable level that can come from solar panels. I'd like to connect all of these together in the world to form a big distributed computer based on solar panels where the computation follows the sun. And so the next thing we need to do is kind of figure out this location transparency of all the processes in the world. For Erlang we know about all the processes on one machine. Given its name, we can send a message to it. But I would like actually to know how to send a message to all the processes that exist on any machine anywhere in the world. And so I think we know how to do that, actually. I mean, we know that there's many man-years of research into distributed hash tables and 1,000 packs of PhDs. We can go and read how to do it. But we have to talk to the network people and we have to talk to the software people and choose one of those PhDs and do it. Build it.
I presume you're heading towards process migration, which is to say that live processes can move around.
Well, not moving at all. We've done that for ages. I mean, we do migrate processes in Erlang on a multi-core. We move them between processes. Yeah, sure. But we don't move them very far. I mean, we don't move processes from here to Australia. And there's a great trade-off, should we be moving the data to the computation or the computation to the data or move them both somewhere in the middle or do these things. So doing some experiments with machine learning to try and figure out what's going on there. And how does the energy usage depend upon the placement of those processes? We do speculative computation, moving the processes around to see what happens. So I think these sort of things like the paralleller and machine learning and those kind of things are very interesting. So. Yeah, so I think it's time for questions, because that's the end of my slides. Thank you.
Can you comment on the relationship between Erlang and Scala? Because I'm just coming up to speed on Scala, and I want to understand what got inherited and what are the differences and commonalities.
I don't know, because I don't really know Scala, but I know they copied the Erlang libraries. Because the guy who did it, I mean, he was told just, hey, look at Erlang and do it like that. So Erlang's influenced quite a few.
Does anybody here knows both?
Sorry?
Does anybody here knows both? Can you make a comment?
So Scala is, it uses the actor model following Erlang, but it's not part of the language, it's simply a library. Scala has very good flexible syntactic support, so they've been able to emulate the Erlang syntax as well to some extent when it comes to message passing and pattern matching on the results, but they don't have anything like the history of OTP, the robustness, the stability, the scalability, and so forth. So they are kind of in a good position to get going on the path, but they'll be playing catch up with Erlang for a long time.
I don't think they have a success slide for Scala like the Erlang success. I mean, they may, but I don't know that.
So Scala is an Erlang wannabe, is that what I mean?
Yeah, that's not fair.
It's alternative on the JVM right now.
Well, no, it's for people who have, for various reasons, have to program inside the JVM. Their corporate structure says you have to program inside the JVM. So Erlang doesn't run inside the JVM efficiently. There is a port of it. If you put Erlang inside the JVM, it will inherit the JVM garbage collector and things like that. So it'll be logically the same, but pragmatically it'll be very different.
What are the semantics of remote failure detection? If a machine isn't responding to pings, I don't know if it failed or if our network failed, or how do you handle that?
Well, there's a heartbeat that's going on, and if some timeout goes, we just assume that machine's dead. And sorry?
And if it wasn't?
Got troubles later. This is the reality, reality bites there. There are certain assumptions you can, somebody said, what assumptions can you make about Erlang and between messages and what's going on? there is an assumption that if you send messages between a pair of processes and you set up one of these links that I talked about, and you don't see any error messages on those links, then you can assume that all the messages got delivered in the same order they were sent. And when I say assume, Hederland had with the provision that if you believe that TCP/IP works. You know, so I mean, you've always got these kind of, well, I can assume this if we assume that TCP/IP works, and then the next level of abstraction say, well, I can assume that if we assume that a proton doesn't come along and sort of change a MD5 checksum in a consistent way, or at some level, turtles all the way down. Something you have to make assumptions about the layer below. So we make not unreasonable assumptions about what's going to happen if things start failing.
And if you're deploying into an environment where you expect a lot of network partitions, it's very easy to kind of write your own network transport layer between separate Erlang nodes instead of using the built-in one.
I have a couple of very basic, dumb questions.
There are no dumb questions.
You talked about, the different, there's a lot of progress on graph algorithms, graph databases. You mentioned machine learning. Do you see any work that is sort of combines Erlang architecture with some of these things? Meaning a lot of graph algorithms work toward improving performance. And one of the aspects of performance is fault tolerance, which was your topic. And
Yeah, well, we have seen, we've seen some actually using visualization techniques to detect bottlenecks and things like that. It turns out if you visualize them, your eyes are very good at seeing what's going on. So there's been some, Concurrency, the company, did some work on that a while back, and I think amazing videos where, this is really cool, because I used to be a physicist. It's like a sort of gas, and you see things flying all over the place. Your eye immediately sees start coloring processes by the number of messages they send and turn them red and then make them bigger and draw these graphs. And I think these techniques for finding out what's going on in your system are coming, and then if we combine that with machine learning or something. We are doing some experiments in machine learning to see, but it's early days at the moment. We're just collecting data. We got some silly ideas. Let's collect some data and run some neural nets on and see what happens. Try moving them around, see if we can learn something. That's beyond state of the art. Yes?
Do in Erlang all processes execute the same code, or is a process more like a function that executes a particular?
It is a function that executes.
Mm-hmm.
And they're all executing different things.
How then do you decide if you need more bandwidth for that particular function? How many processes you need to spawn for that function, and how do you do load balancing to know where to send?
That's part of your application. Erlang gives you no support for that.
Gives you no
support for that. You have to design that into your application itself. You as the designer of that thing have to say, okay, I know this takes a lot of time, so I will parallelize that using functions or something. There's no automatic parallelization. You could choose to. If you've written it in a functional style with maps and folds and things, you could just put some p maps to parallel map and p fold in your program. But I think, so there's a lot of projects trying to automate that stuff, and there've been projects to automatically discover parallelism ever since I did Fortran, in 1975. And I think none of them have improved anything by more than about 15% or something. So I think you need some intuition as to what's going on. And I would always say my intuition, I have no intuition at all as to where bottlenecks are or where performance things. I have to write programs and measure. And I just don't, I don't like, I get all these questions on the Erlang mailing list. I've got a lot of data and lots of this and big this, and I say, no, don't use words like lots, big, what's big? Because I'm thinking, big petabytes or terabytes, it's in your head. We use all these words and we lots of data, megabytes of data, terabytes of data. It has to be fast. Transactions per second. How many per millisecond do you want per machine? How many machines have you got? How much memory have you got? Oh, I ask a load of questions. How many machines have you got? How much memory have they got? What's the clock rate? How big are the packets? Then you can start answering the questions. And then you have to sort of take your application and put those two in relationship to each other. But that's what you do later. First of all, you write it as beautifully as possible without any regard to efficiency. And then you tweak a bit if necessary.
One more. Yeah. So I assume you usually have a lot more processes than hardware units to execute them on.
Yes.
So what happens with those messages that are sent to processes that are not running? Where are those stored?
Oh, in the mailboxes of the process. I mean, the process not running are just in a round-robin queue. Eventually, they will run.
So the mailbox is always available?
Yeah.
And this is managed by a
the runtime
central process, or who manages those mailboxes?
It's one mailbox per process. These okay, when I'm using words like mailbox and process, don't think Unix processes and big, heavy things. Don't think big, heavy, ugly threads. Think very, very small things. I mean, process is about 350 bytes. Its mailbox is however much space it needs to store the messages that come to it. You have to also, when you're designing your application, make sure you don't overflow these mailboxes, and make sure that, if you've got a sender and a receiver, that there's no flow control either. If you want flow control, you have to program it yourself.
Processes move on and off the run queue based on their mailbox status.
Yes, yeah, sure. And whether they're CPU bound. So they get, I think like, used to be 500 reductions. The reduction was one function call. It's now about 2,000. They get to call 2,000 functions, and then if they're not finished, they just get stuck in the run queue. Or if they get to a receive statement and there's nothing to do, they're taken out of the run queue completely. And then the next time a message comes, they're put in a save queue, they're put back into the run queue and rescheduled. So I mean, Erlang is much more like an operating system than a programming language. In fact, Erlang on Zen boots the operating system, runs an Erlang application, and then goes back to sleep in about 400 milliseconds. That's the time to get a complete functioning system up and running, do something, and then go away. And that can scale out horizontally onto S3 and things like that. So a lot of people who are building things like WhatsApp are taking things like Erlang on Zen, deploying it in a horizontally scalable platform so they can boot up thousands of these things. They will grow and come into service within 400 milliseconds and be doing their job, and then they go away again.